Picture this, a universe so vast that it contains more stars than all the grains of sand on every beach on Earth combined. Yet every one of those stars, every planet, every atom in your body, all of it traces back to a single moment of explosive creation. How did everything we see, touch, and know spring from absolute nothingness? That's the greatest mystery of all, and today we're diving deep into the unknown. This video will explore 30 mind-blowing questions about the birth of the cosmos, from the explosive spark of the Big Bang to the hidden forces shaping our universe right now. We'll weave together cutting-edge science, tantalizing theories, and the sheer wonder of existence itself to peel back the layers of cosmic origins. Whether you're a space enthusiast or just curious about how it all began, prepare to have your perspective stretched wider than the expanding universe. The journey starts now. Let's unravel the ultimate mystery together. Now, let's tackle the very first mystery, what set the universe in motion. The Big Bang Theory tells us that everything began with an unimaginably hot, dense point around 13.8 billion years ago. But what caused that initial explosion? Scientists are still piecing together the puzzle, but some compelling ideas have emerged. One leading theory suggests that tiny quantum fluctuations, random ripples in the fabric of empty space, could have sparked the expansion. Think of it like a cosmic game of chance, where the right random jitter tipped the scales from nothingness into creation. Another mind-bending idea is the multiverse hypothesis, which proposes that our universe is just one bubble among countless others in a vast, bubbling cosmic foam. If that's true, the Big Bang might have been a collision or a split from another universe entirely. Then there's the older but still intriguing concept of the primeval atom, a single, ultra-dense speck of matter that somehow unraveled into everything we know today. So why does the Big Bang remain the go-to explanation, even with these unanswered questions? Simply put, it fits the evidence better than any alternative. The cosmic microwave background, the faint afterglow of the Big Bang, lines up perfectly with predictions. The way galaxies are moving apart, the abundance of light elements like hydrogen and helium, all of it points back to that explosive beginning. Yet the quest for what came before, or what ignited it all, continues to push the boundaries of human knowledge. And that's what makes this question so thrilling. It reminds us that the greatest mysteries are still out there, waiting to be unraveled. Next, we'll explore an even more perplexing thought. Was there anything before the Big Bang? Because if time itself began then, how do we even begin to make sense of what came before nothing? Now, let's stretch our imaginations even further. What if the Big Bang wasn't the true beginning, but just a chapter in a much grander story? The idea of a cyclic universe suggests that our cosmos might be caught in an endless loop of expansion and contraction. Picture a cosmic heartbeat where each Big Bang is followed by a big crunch, collapsing everything back into a dense point only to explode anew. Some theories even propose that the collisions of massive, higher-dimensional brains, floating membranes in a larger space, could trigger new universes like ripples from stones tossed into a pond. Then there's the mind-bending question of nothingness. If time itself began with the Big Bang, can we even speak of a before? Philosophers and physicists debate whether nothing might not be empty at all, but a seething quantum foam where universes pop in and out of existence. Imagine trying to ask what's north of the North Pole. The question might not even make sense because the framework we're used to breaks down. Here's where it gets really wild. If time didn't exist before the Big Bang, then causality, the idea that every effect has a cause, might not apply. There'd be no before to cause the after. Theories like loop quantum gravity toy with the idea of a quantum bridge, linking our universe to a previous state, while others, like Hawking's no-boundary proposal, suggest the universe simply has no starting edge, much like the Earth has no true starting point. One thing's certain, this question blurs the line between physics and philosophy. reminding us that some mysteries might forever hover just beyond our grasp. Next up, we'll tackle an equally baffling idea. How did the universe manage to expand faster than light itself? All right, let's tackle this cosmic head-scratcher. How did the universe pull off something that seems downright impossible, expanding faster than light? At first glance, it sounds like breaking the universe's own speed limit. But here's the twist: the rules we're used to don't quite apply when spacetime itself is doing the stretching. Enter cosmic inflation, a theory that rewinds the cosmic clock to a fraction of a second after the Big Bang. Picture this: the universe wasn't just expanding, it was stretching at an unimaginable rate, doubling in size over and over again in the blink of an eye. This wasn't stuff moving through space, it was space itself stretching like dots on an inflating balloon racing apart without actually moving. That's the key. Light speed limits how fast objects can travel through space, but they don't cap how fast space can expand. During this inflationary epoch, the universe likely grew by a factor of 10 to the power of 26 in less than a trillionth of a second. To put that in perspective, imagine a subatomic particle suddenly ballooning to the size of a galaxy. Wild, right? This explosive stretch explains why the cosmos looks so uniform. Tiny patches of space got blown up to enormous scales, smoothing out any wrinkles. Now, why doesn't this break Einstein's rules? Because inflation isn't about things moving faster than light. It's about the fabric of reality itself stretching faster than light could cross it. Think of it like running on a treadmill that's speeding up faster than you can sprint. You're not breaking any personal records, but the ground beneath you is. This theory isn't just a nifty idea, it's backed by clues like the cosmic microwave background's eerie uniformity and the universe's large-scale structure. Without inflation, we'd struggle to explain why the cosmos looks the way it does. And with that, we've got another piece of the puzzle. Next up, the mysterious force that's not just stretching the universe but doing it faster and faster: dark energy. Now, let's turn our attention to one of the most baffling forces in the cosmos: dark energy. Imagine watching a car speed up without anyone pressing the gas pedal. That's essentially what astronomers observed in the late 1990s when they discovered that the universe isn't just expanding, it's accelerating. This revelation turned cosmology on its head and earned researchers the Nobel Prize in Physics in 2011. So, what's behind this cosmic acceleration? Enter dark energy, an invisible force making up roughly 68% of the universe's total energy. Unlike gravity, which pulls things together, dark energy acts like a repulsive force, pushing space itself apart. But here's the catch: we don't actually know what it is. The leading idea is vacuum energy, a kind of background energy woven into the fabric of space. According to quantum mechanics, even empty space isn't truly empty, it's fizzing with particles popping in and out of existence, and this activity might be driving the expansion. Another contender is quintessence, a dynamic field that changes over time, unlike vacuum energy's constant push. Some theories suggest it could weaken or strengthen, altering the universe's fate. But here's the problem: while vacuum energy fits some observations, its predicted strength is off by a factor of 10 to the power of 120. That's like expecting a whisper and hearing a supernova instead. The evidence for dark energy comes from studying distant supernovae, the explosive deaths of stars. By measuring their brightness, astronomers realized these explosions were dimmer than expected, meaning space had stretched more than predicted since the light left them. This discovery confirmed the universe's expansion wasn't slowing down, it was speeding up thanks to dark energy's mysterious influence. Whether it's vacuum energy, quintessence, or something entirely unforeseen, dark energy remains one of cosmology's biggest puzzles. And with that, we're left wondering what other secrets is the universe hiding. Next up, we'll explore the invisible scaffolding holding galaxies together: dark matter. Now, stepping into the shadows of the cosmos, let's unravel another invisible giant, dark matter. Picture this: you're watching a merry-go-round spin, but instead of slowing down at the edges, the outer horses are whipping around just as fast as the inner ones. That's exactly what astronomers noticed with galaxies. Stars on the outer edges orbit just as quickly as those near the center, defying Newton's laws. The only explanation, an enormous halo of invisible matter, dark matter, must be tugging on them with its gravity, keeping the galaxy from flying apart. But how do we know dark matter exists if we can't see it? Enter gravitational lensing, nature's magnifying glass. When light from distant galaxies passes through a cluster of dark matter, its path bends, distorting the images behind it like a cosmic funhouse mirror. By measuring these distortions, scientists can map dark matter's distribution, revealing vast webs stretching across the universe. So what could dark matter be made of? Leading candidates include WIMP, weakly interacting massive particles, theoretical particles that barely interact with ordinary matter except through gravity. Then there are actions, ultralight particles that could flow through you like a ghostly breeze. Unlike atoms, which make up stars, planets, and us, dark matter doesn't emit, absorb, or reflect light, hence its elusive nature. Here's the twist: while ordinary matter makes up less than 5% of the universe's content, dark matter outweighs it 5 to 1. Think of it as the unseen scaffolding holding galaxies together, shaping the cosmic landscape. Without it, the universe as we know it wouldn't exist. Yet, after decades of searching, we still haven't directly detected it, leaving one of science's greatest riddles unsolved. Next, we'll journey back to the universe's infancy to ask, how did the first atoms form after the Big Bang? Now, let's turn back the cosmic clock to a time when the universe was just taking its first breaths, when the simplest building blocks of everything we know began to assemble. In the scorching aftermath of the Big Bang, the universe was a seething soup of particles too hot and chaotic for atoms to exist. But as it expanded and cooled, something remarkable happened. The very first atoms began to form. Imagine the universe was only a few minutes old at this point, still blisteringly hot, but just cool enough for protons and neutrons to start sticking together. This process, called nucleosynthesis, is where the first atomic nuclei were born. Protons, which are positively charged hydrogen nuclei, paired up with neutrons to form deuterium, a heavy version of hydrogen. These deuterium nuclei then collided and fused, creating helium nuclei. In just those first 20 minutes, nearly all the hydrogen and helium in the universe came into existence, hydrogen making up about 75%, helium around 25%, with only trace amounts of lithium and beryllium. But here's the catch: nothing heavier was made. Why? The universe was expanding too fast and the temperature dropped too quickly for larger nuclei to form. It wasn't until much later, when the first stars ignited, that the extreme heat and pressure in their cores forged heavier elements like carbon, oxygen, and iron. That means everything in you, the calcium in your bones, the iron in your blood, was cooked inside ancient stars billions of years after the Big Bang. So while those first few minutes gave us the hydrogen and helium that fuel the cosmos, it took the fiery furnaces of stars to build the elements that make planets and life possible. Next, we'll explore the echo of creation itself, the cosmic microwave background, and how it reveals the universe's earliest moments. Now, let's step into one of the most profound pieces of evidence we have for the Big Bang: the cosmic microwave background, or CMB. Picture this as the universe's baby photo, a faint glow that fills every corner of space, carrying whispers from a time when the cosmos was just 380,000 years old. Before this point, the universe was too hot and dense for light to travel freely. It was a swirling plasma of particles and energy constantly colliding. But as expansion cooled everything down, electrons and protons finally combined to form neutral hydrogen atoms, allowing light to break free for the first time. That ancient light has been traveling ever since, stretched by the expanding universe into microwaves we detect today. It was accidentally discovered in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who were puzzled by a persistent static noise in their antenna. After eliminating every possible earthly cause, even cleaning out pigeon nests, they realized they'd stumbled upon the echo of creation itself. This discovery earned them a Nobel Prize and cemented the Big Bang theory as the leading explanation for our universe's origins. But the CMB isn't just a uniform glow. It's speckled with tiny temperature variations, hotter and colder patches that tell an incredible story. These fluctuations are the seeds of cosmic structure, slight density differences that, over billions of years, grew into the galaxies and galaxy clusters we see today. Satellites like the Cosmic Background Explorer and Planck have mapped these patterns in exquisite detail, revealing the universe's blueprint at its most primordial stage. Think of it like a fossilized ripple in space-time, preserving the moment when the universe transitioned from a fiery plasma to a transparent sea of light. And here's the kicker: without those tiny imperfections in the CMB, gravity wouldn't have had anything to work with. No galaxies, no stars, no us. So while it might seem like just a faint microwave hum, this afterglow is literally the foundation of everything. Next, we'll tackle why the universe looks so remarkably uniform across vast distances, and how inflation theory solved one of cosmology's biggest puzzles. Here's how the next section would flow naturally from where we left off. So, if the cosmic microwave background shows us the universe's early imperfections, why does the cosmos look so eerily similar in every direction? This is the horizon problem, one of the biggest head-scratchers in cosmology. Imagine two regions of space so far apart that light from one could never have reached the other since the Big Bang, yet they share almost identical temperatures. How it's like walking into two separate bakeries on opposite sides of the planet and finding identical loaves of bread down to the last crumb. Without some cosmic cheat code, this shouldn't be possible. Early cosmologists struggled with this. If the universe grew steadily from the Big Bang, those distant regions wouldn't have had time to share heat or information. They'd be like strangers separated by an insurmountable distance. But then came inflation theory, a game-changer proposed in the 1980s. Picture the universe in its first fraction of a second, a tiny, subatomic speck, hot and dense, where quantum fluctuations created microscopic differences. Then inflation kicked in, a sudden, exponential expansion that stretched space faster than light itself. That hyper-stretching took those tiny neighboring regions and blew them up to cosmic scales, smoothing out irregularities while locking in that uniform temperature. It's like inflating a balloon with a few faint wrinkles. Once it expands massively, those wrinkles become vanishingly small. Inflation didn't just solve the horizon problem, it also explained why the universe appears flat and why those CMB fluctuations exist at all. Here's the twist: without inflation, the cosmos might look wildly different from place to place. Instead, we live in a universe where even the farthest corners whisper the same temperature, thanks to that brief but spectacular growth spurt. Up next, we'll explore cosmic strings and other bizarre relics that might have been left behind by those early universe gymnastics. Now, let's untangle another fascinating mystery left over from the universe's infancy: cosmic strings and other space-time defects. Think of these as microscopic cracks or scars in the fabric of the cosmos, formed when the newborn universe cooled and underwent dramatic phase transitions, much like ice crystals forming in water. Among these relics, cosmic strings stand out: hypothetical, super-dense filaments thinner than an atom but stretching across the entire universe, carrying immense gravitational pull. If real, they'd be like invisible fishing lines left over from the Big Bang, warping space around them so intensely that they could bend light or even create double images of distant galaxies. Then there are domain walls, vast sheet-like structures separating regions of space with different properties, and magnetic monopoles, isolated north or south magnetic poles that shouldn't exist under normal physics. While none of these defects have been directly observed, their existence is predicted by theories like grand unification, which suggests the fundamental forces were once merged in the early universe's extreme heat. Here's where it gets even more intriguing. Cosmic strings, if they exist, might leave behind detectable ripples in spacetime called gravitational waves. Unlike the fleeting signals from black hole mergers, these waves would hum at a steady, ultra-low frequency, a whisper from the universe's first moments. Future observatories like the Laser Interferometer Space Antenna, or LISA, could potentially pick up this cosmic vibration, offering a backstage pass to how spacetime itself fractured as the universe cooled. So while these defects remain theoretical, their discovery would rewrite our understanding of cosmic history, revealing how the universe's most violent transitions shaped the orderly cosmos we see today. Next up, we'll grapple with an even bigger question: whether time itself had a beginning. Stay tuned. Let's take a step even further back into the realm where time itself might not have existed. The question of whether time had a beginning is one of the most mind-bending puzzles in cosmology. If the Big Bang marked the birth of space and time, what does that mean for the concept of before? After all, if time didn't exist, the word before loses all meaning. Some theories, like loop quantum gravity, suggest that the universe could have emerged from a timeless state, a quantum foam where space and time were tangled and fractured, only snapping into the orderly flow we know today after the Big Bang. Others, like Stephen Hawking's no-boundary proposal, imagine time behaving like directions on a globe. Just as there's no edge at the North Pole, there's no starting point for time. Hawking even introduced the idea of imaginary time, a mathematical trick where time acts more like another dimension of space, smoothing out the singularity at the universe's birth into something more manageable. But not everyone agrees. Some physicists argue that time might have stretched infinitely backward, with the Big Bang just one moment in an eternal cycle. The truth is, we're still grappling with the very definition of time on cosmic scales, and until we find a way to test these ideas, perhaps through quantum gravity experiments or deeper cosmic observations, this mystery will keep us questioning the very fabric of reality. Up next, we'll explore how the universe went from a swirling, formless soup to the intricate web of galaxies we see today. Now, let's zoom in on the cosmic transformation that turned a chaotic, superheated soup into the breathtaking galaxies we see today. Picture the early universe, a searing, dense plasma where particles zipped around at incredible speeds. But hidden within that chaos were tiny ripples, faint variations in density that would one day shape the cosmos. These ripples, imprinted in the cosmic microwave background, were like cosmic blueprints, marking where matter would eventually clump together under gravity's relentless pull. Dark matter played the role of the universe's invisible architect, while ordinary matter, the stuff we see, was buffeted by radiation pressure. Dark matter, unaffected by light, began collapsing first. Its gravitational wells acted as traps, gathering ordinary matter into their grasp. Over hundreds of millions of years, these pockets grew denser, hotter, and more massive, eventually igniting the first stars and galaxies. Computer simulations show this process in stunning detail, revealing a pattern called hierarchical clustering. Small structures merge to form larger ones, like streams feeding into rivers. Dwarf galaxies collided and combined, building the majestic spirals and ellipticals we recognize today. It's a story of cosmic teamwork where dark matter's scaffolding and ordinary matter's glow came together to paint the universe with light. Next up, we'll confront one of the most profound questions of all: what destiny awaits our universe in the far, far future? Stepping beyond the birth of galaxies, we arrive at a question that stretches our imagination to the very end of time. What ultimate fate awaits our universe? The answer hinges on a cosmic tug-of-war, with dark energy as the mysterious force tipping the scales. One possibility is the Big Freeze, also called heat death. Here, dark energy keeps pushing galaxies apart until the universe becomes a vast, cold graveyard. Stars burn out, black holes evaporate, and even atoms might decay, leaving only a faint whisper of radiation in an endless void. But what if gravity fights back? In the Big Crunch scenario, dark energy weakens over time, allowing gravity to reverse the expansion. Galaxies would collide, temperatures soar, and the universe collapses into a singularity, a mirror of the Big Bang, perhaps triggering a new cycle. Then there's the more violent Big Rip. If dark energy grows stronger, it could tear apart galaxies, then solar systems, even atoms, shredding spacetime itself in a catastrophic finale. Or consider vacuum decay. A quantum bubble of true vacuum could form, rewriting the laws of physics at light speed, erasing reality as we know it. Which fate is most likely? It depends on dark energy's true nature. Current data favors the Big Freeze, but the universe loves surprises. One thing's certain: the cosmos won't fade quietly. Up next, we'll venture into even stranger territory. Could our universe be just one of countless others? Now, let's shift our gaze beyond the edges of our own universe and ask, could there be others out there? The idea of a multiverse isn't just science fiction. It's a serious scientific hypothesis with several compelling theories backing it up. First, there's the inflationary multiverse. This theory suggests that during the rapid expansion of our early universe, some regions of space stopped inflating while others kept going, creating countless bubble universes. Each of these bubbles could have its own unique laws of physics, making them wildly different from ours. Then there's the string theory landscape. String theory proposes that tiny, vibrating strings make up all of reality, but it also requires extra dimensions, up to 10 or 11. Some physicists argue that these extra dimensions could fold into countless configurations, each forming its own separate universe with different physical constants. And don't forget the quantum multiverse. Stemming from quantum mechanics, this idea suggests that every time a quantum event occurs, like an electron choosing a path, the universe splits, creating parallel realities where every possible outcome plays out. But here's the big question: can we ever test these ideas? Some critics argue that if other universes are beyond our observable reach, the multiverse isn't falsifiable, meaning it falls outside the realm of science. Others point to potential clues, like odd patterns in the cosmic microwave background that might hint at collisions with other bubble universes. The debate rages on, but one thing's clear: the multiverse pushes the boundaries of our imagination and our understanding of reality. Up next, we'll tackle another cosmic puzzle. Why is there so much more matter than antimatter in the universe? Now, let's unravel one of the universe's most puzzling imbalances. Why does matter dominate over antimatter? If the Big Bang had created equal amounts of both, they should have annihilated each other completely, leaving behind a sea of pure energy. Yet here we are, in a universe filled with galaxies, stars, and planets. So what tipped the scales? The answer might lie in a process called baryogenesis. According to physicist Sakharov, 3 key conditions had to be met for matter to win out. First, the universe needed a mechanism to produce more particles than antiparticles, something that breaks the usual symmetry between them. Second, this process had to occur when the cosmos was hot and dense enough for particle interactions to matter. And third, it had to happen out of equilibrium, meaning the universe couldn't have been in a perfectly balanced state at the time. One of the leading clues comes from something called CP violation. In particle physics, C stands for charge conjugation, which swaps particles with their antiparticles, and P stands for parity, which flips their spatial orientation. Normally, the laws of physics should treat particles and antiparticles symmetrically, but experiments show they don't. For example, certain rare decays of particles called kaons and B mesons happen slightly more often for matter than antimatter. This tiny asymmetry, observed in labs like CERN, might hint at how the early universe favored matter. But here's the catch. The amount of CP violation we've found so far isn't nearly enough to explain the overwhelming amount of matter we see today. That leaves scientists scrambling for other explanations, like undiscovered particles or forces that played a role in those critical first moments. This mystery isn't just academic. Solving it could reveal fundamental truths about how reality itself is built. Up next, we'll explore another cosmic blueprint, the shape of the universe itself. Shifting our gaze from the imbalance of matter to the cosmic canvas itself, let's tackle a question that bends the mind. What shape does the universe take? Is it flat like a sheet of paper, closed like a sphere, or stretched open like a saddle? The answer isn't just about geometry, it's woven into the fabric of spacetime itself. According to Einstein's theory of general relativity, the universe's shape depends on its total mass and energy. Imagine spacetime as a trampoline. Place a bowling ball in the center and the fabric curves inward. This is gravity's grip. Now scale that up to the entire cosmos. If the universe has enough matter and energy, it could curve back on itself like a giant four-dimensional sphere, a closed universe. In this scenario, if you traveled far enough in one direction, you'd eventually loop back to where you started, like circumnavigating Earth. But if the cosmos doesn't have enough density, it might curve outward, forming an open universe shaped like an infinite saddle. Here, parallel lines would diverge over vast distances, and space would stretch forever without end. Then there's the Goldilocks scenario, a flat universe where the density is perfectly balanced at what's called the critical density. Measurements from the cosmic microwave background, especially by missions like Planck, suggest our universe is astonishingly close to this flatness, with space obeying the rules of classic Euclidean geometry on large scales. But here's the twist. Even if the universe is flat, that doesn't necessarily mean it's infinite. It could still be finite but unbounded, like a video game where exiting one side teleports you to the other. The real kicker, dark energy and dark matter, which make up over 95% of the universe's content, hold the keys to this cosmic puzzle. Their mysterious properties could still tilt the scales toward a shape we haven't fully mapped yet. Next, we'll dive into the gravitational giants that lurk in the cosmos, black holes, and how they might have shaped the universe's evolution from the very beginning. Now, let's turn our attention to one of the most fascinating forces in the cosmos, black holes, and how these gravitational monsters have left their mark on the universe's story. Far from being just cosmic vacuum cleaners, black holes are active players in shaping galaxies and beyond. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These giants, weighing millions to billions of times the mass of our Sun, aren't just sitting quietly, they're pulling the strings of galactic evolution. When galaxies collide, their central black holes eventually spiral toward each other, creating gravitational waves, ripples in spacetime that we can now detect. But before they merge, these black holes stir up chaos, heating surrounding gas and triggering bursts of star formation. In some cases, they even act like cosmic stop signs, halting star birth by blasting out powerful jets of energy that clear away the raw materials needed for new stars. It's a delicate balance between creation and destruction, with black holes playing referee. Then there's the mind-bending phenomenon of Hawking radiation, where black holes aren't entirely black. Quantum effects near a black hole's edge allow particles to escape, causing the black hole to slowly shrink over eons. This idea ties back to the early universe, where tiny primordial black holes might have formed, and some could still be lurking today, possibly even accounting for part of dark matter. And let's not forget the black hole information paradox, a puzzle that challenges our understanding of reality itself. If matter falling into a black hole vanishes forever, what happens to the information it carried? This question bridges the gap between quantum mechanics and gravity, with implications stretching back to the universe's first moments. Black holes, it seems, aren't just shaping galaxies, they're shaping the very frontiers of physics. Next, we'll explore an idea that sounds straight out of science fiction. Could some of these black holes have been born in the universe's infancy, and might they be hiding in plain sight today? Now, imagine a universe so young and dense that pockets of matter could collapse directly into black holes, no dying stars required. These are primordial black holes, thought to have formed in the first chaotic seconds after the Big Bang. Unlike the black holes born from collapsing stars, these ancient relics could be as small as an atom or as massive as a mountain, scattered across the cosmos like invisible seeds. Here's where it gets even more intriguing. Some scientists believe these primordial black holes might solve one of astronomy's biggest puzzles, the nature of dark matter. We know dark matter's gravity holds galaxies together, but we've never detected the particles it's supposedly made of. Primordial black holes, though, wouldn't need to be new particles at all. If enough of them formed in the early universe, their collective gravity could perfectly mimic the effects of dark matter. But how would we find them? Some might reveal themselves by bending light from distant stars, a phenomenon called microlensing. Others could collide, sending out gravitational waves we can detect. And if they're very small, they might even explode in a final burst of Hawking radiation, leaving behind a telltale flash. So far, searchers haven't turned up definitive proof, but the hunt is far from over. This idea bridges two cosmic mysteries, black holes and dark matter, in a way that challenges our understanding of the universe's infancy. Whether or not primordial black holes are the answer, their story reminds us that the cosmos often hides its secrets in plain sight. Next, we'll see how even the tiniest quantum ripples in the early universe grew into the vast galactic structures we see today. Shifting our focus from ancient black holes to the very fabric of the early universe, let's zoom in on something almost unimaginably small: quantum fluctuations. Picture the newborn cosmos as a bubbling sea of energy, where particles flicker in and out of existence on the tiniest scales. These fleeting fluctuations might seem insignificant, but they held the seeds of everything we see today. So how did these microscopic ripples become the vast galaxies around us? The key was inflation, a period when the universe expanded faster than light, stretching those tiny quantum wrinkles into enormous density variations. Think of it like blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots grow into large patterns. In the same way, inflation magnified those initial quantum hiccups, creating regions where matter was slightly denser than average. Over billions of years, gravity got to work. Those denser patches pulled in more and more gas and dark matter, slowly growing into the first stars and galaxies. It's a staggering thought. The grand structures of the cosmos, from spiraling galaxies to colossal superclusters, all trace back to quantum jitters smaller than an atom. This cosmic transformation bridges two seemingly unrelated worlds, the subatomic realm of quantum mechanics and the vast scale of galaxies. It's a reminder that the universe loves turning the smallest details into its biggest wonders. Next, we'll explore another puzzling force shaping the cosmos: vacuum energy, and why its behavior defies all expectations. Now let's peel back another layer of cosmic mystery: vacuum energy, the invisible force humming in the very fabric of empty space. Imagine a universe where even nothingness isn't truly empty. According to quantum mechanics, so-called empty space is a seething soup of temporary particles popping in and out of existence. This is zero-point energy, the lowest possible energy a quantum system can have, and it's anything but zero. Here's where things get baffling. When scientists tried to calculate how much energy this quantum frenzy should contribute to the universe, their math suggested an absurdly huge number, enough to rip spacetime apart instantly. Yet observations show the actual effect is staggeringly tiny, weaker than predicted by a factor of 1 followed by 120 zeros. This jaw-dropping mismatch is called the cosmological constant problem, and it's one of physics' most embarrassing puzzles. Why the disconnect? Some argue our math is missing a key piece, like an unknown symmetry that cancels out most of vacuum energy's effects. Others wonder if multiple universes exist with random energy values, and we just lucked into one where the number is survivably small. Whatever the answer, vacuum energy's subtle push is now credited with accelerating the universe's expansion, a discovery that earned a Nobel Prize. So next time you stare at the night sky, remember, the vast emptiness between stars isn't passive. It's alive with invisible energy, quietly steering the fate of the cosmos. Up next, we'll ask if the universe itself could be a cosmic hologram, a projection of deeper, hidden laws. Let's take a step into one of the most mind-bending ideas in modern physics. What if our universe is nothing more than a hologram? Not the sci-fi kind with floating green grids, but a cosmic illusion where everything we see, from galaxies to the stars in your eyes, is actually encoded on a distant, two-dimensional surface. This wild concept is called the holographic principle, and it's not just speculation, it's rooted in some of the most advanced physics we have. The idea sprouted from black hole research. When scientists calculated how much information a black hole could hold, they found something shocking. Its maximum data storage wasn't defined by its volume, like you'd expect, but by the surface area of its event horizon. That's like saying everything inside a box is determined by what's painted on its outside. This led theorists to propose a radical idea: maybe our entire universe works the same way. Here's where things get even stranger. In the late 1990s, physicists discovered something called anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. It's a mathematical bridge showing how a higher dimensional world, like our three-dimensional space, could be perfectly mirrored by physics playing out on a lower dimensional boundary. Think of it like a DVD. The movie you watch in 3 dimensions is actually stored as flat data on the disk's surface. So could we be living in a hologram? No experiment has proven it yet, but the math checks out. Some physicists even suggest that if the holographic principle is true, spacetime itself might be pixelated at the tiniest scales, like a cosmic version of your TV screen. It's a humbling thought. Every star, every planet, and even you might just be shadows cast by deeper, hidden laws written on the edge of reality. Next up, we'll explore what brought the inflationary epoch to a close, the moment our universe went from a whisper to a roar. Now, shifting our gaze to another cosmic turning point, let's unravel what brought the universe's rapid inflationary expansion to a sudden halt. Picture this: the early universe was stretching at an unimaginable speed, doubling in size countless times in mere fractions of a second. But then, just as abruptly as it began, inflation stopped. What slammed the brakes on this hyper-expansion? The answer lies in something called the graceful exit problem, and it's tied to a mysterious field known as the inflaton. The inflaton field was the engine behind inflation, driving spacetime to stretch exponentially. But like any energy source, it couldn't last forever. As this field lost energy, it began to decay, releasing its stored power in a burst of particles and radiation. This moment, known as reheating, was like flipping a cosmic switch, transforming the cold, empty universe of inflation into the seething, particle-filled cauldron of the hot Big Bang. But here's where it gets tricky. Scientists still debate exactly how this decay happened. Some theories suggest the inflaton field oscillated, like a spring winding down, shedding energy with each vibration. Others propose it collapsed suddenly, like a bubble popping, releasing energy in a single explosive event. Whatever the mechanism, this transition had to be just right, too fast, and the universe wouldn't have had time to smooth out, too slow, and it might not have reheated enough to kickstart the Big Bang's fireball. The legacy of this cosmic pivot is all around us. The particles born during reheating became the building blocks of everything: stars, planets, even us. And while we can't yet rewind the clock to witness inflation's end directly, clues hide in the faint ripples of the cosmic microwave background, the afterglow of the Big Bang. Up next, we'll tackle another puzzle. Are the laws of physics the same everywhere, or could they change across the cosmos? Now, let's turn to one of the most fundamental questions in cosmology. Are the laws of physics the same everywhere, or could they change across space and time? Imagine if the speed of light or the strength of gravity wasn't constant but shifted as you moved through the universe. It sounds like science fiction, but some scientists seriously consider this possibility. For centuries, we've assumed the laws of physics are universal, the same in distant galaxies as they are here on Earth. This principle is the bedrock of cosmology, allowing us to study the universe with confidence. But what if that's not entirely true? Some theories suggest that certain constants, like the fine structure constant governing electromagnetism, might vary slightly over vast cosmic distances. Observations of distant quasars have hinted at tiny discrepancies, though the evidence remains hotly debated. The stakes are high. If physical laws aren't immutable, it would rewrite our understanding of reality. This ties into the concept of fine-tuning the eerie precision of the universe's constants that allow life to exist. Tweak gravity just a bit stronger, or the electron's charge slightly weaker, and stars, planets, and life itself might never have formed. The anthropic principle offers one explanation. Maybe we observe these exact values because they're the only ones that permit our existence. But here's the twist: could there be regions of the cosmos where the rules are different? Some multiverse theories suggest so, with each universe in the greater multiverse having its own unique physics. While we can't yet test these ideas directly, they challenge us to rethink whether our laws are truly universal or just a local quirk of our cosmic neighborhood. Next, we'll journey back to the dawn of the first stars, colossal, short-lived giants whose fiery births lit up the cosmos and forged the elements that make up everything we see today. Stepping into the cosmic dawn, we arrive at a pivotal moment: the birth of the first stars. These weren't just any stars, they were titans, hundreds of times more massive than our sun, blazing with raw intensity in a universe still in its infancy. Scientists call them population 3 stars, and they were unlike anything we see today. Why? Because they formed from the purest ingredients, hydrogen and helium, with not a trace of heavier elements like carbon or oxygen. Picture a cosmos fresh out of its dark ages, shrouded in gas but silent, without a single star to light it up. Gravity began pulling together these pristine clouds of hydrogen, compressing them until the pressure and heat at their cores became unimaginable. Then ignition, nuclear fusion sparked, and the first starlight pierced the darkness. But these stars burned fast and furious, living only a few million years before meeting explosive ends. Their deaths were just as transformative as their births. When these giants exploded as supernova, they unleashed a storm of newly forged elements: carbon, oxygen, iron, scattering them across the cosmos. This stardust became the building blocks for everything that followed: later generations of stars, planets, and even us. Without those first stars, the universe would have remained a featureless void, devoid of the complexity that makes life possible. So next time you look up at the night sky, remember, you're witnessing a legacy that began with those primordial giants. Their light may be long gone, but their echoes shaped the universe we call home. And speaking of cosmic transformations, let's delve into the very fabric of reality. What is space-time made of, and why does it behave the way it does? That's where our journey takes us next. Now, let's stretch our minds even further and ask, what exactly is the fabric of reality woven from? Space-time isn't just an empty stage where the universe's events play out. It's an active, dynamic entity with its own structure. But what is it made of? The answer depends on who you ask. Einstein's theory of general relativity paints space-time as a smooth, flexible fabric, warped by mass and energy like a trampoline bending under a bowling ball. But when we zoom into the tiniest scales, this elegant picture starts to fray. Enter quantum mechanics, where things get messy. Here, spacetime might not be smooth at all. Some theories, like loop quantum gravity, suggest spacetime is made of tiny, indivisible loops. Think of it as a cosmic mesh, with each thread representing the smallest possible piece of reality. Then there's string theory, which imagines everything, including spacetime, as vibrations of impossibly small strings. These strings wouldn't just move through spacetime. They'd be part of its very essence, humming at different frequencies to create the particles and forces we know. But here's the twist. At our everyday scale, these wild ideas collapse back into the familiar smooth spacetime Einstein described. It's like looking at a piece of fabric up close. You see threads and gaps, but from a distance it appears seamless. The challenge testing these theories, the scales involved are so unimaginably small that even our most advanced particle smashers can't probe them directly. Yet clues might lie in cosmic phenomena like black holes or the faint echoes of the Big Bang itself. So while we don't yet know spacetime's true nature, one thing's certain: it's far stranger than we ever imagined. And that strangeness doesn't stop here. Next, we'll tackle another head-scratcher. Why does our universe have exactly 3 spatial dimensions? The answer might just redefine how we see reality itself. Transitioning now to another fascinating puzzle. Why does our everyday reality unfold in exactly 3 spatial dimensions? It feels intuitive. Length, width, and depth are all we've ever known. But mathematically, the universe could have functioned with any number of dimensions. So what makes 3 so special? One compelling answer comes from string theory, which suggests the cosmos might actually have more dimensions, up to 10 or 11 in some versions. But here's the catch: these extra dimensions are thought to be compactified, curled up so tightly that they're imperceptible at our scale. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line, but up close, you see its circular surface, revealing a hidden dimension. Similarly, these extra dimensions could be folded into shapes too tiny for us to detect, leaving only the familiar 3 to shape our experience. But why 3? Stability might hold the key. Physics reveals that in universes with more than 3 spatial dimensions, the orbits of planets or even atoms wouldn't stay stable. Gravity's pull would weaken so drastically with distance that solar systems couldn't form, and complex structures like galaxies would fly apart. Even fundamental forces like electromagnetism behave differently in higher dimensions, making the chemistry of life impossible. In other words, 3 dimensions strike a delicate balance, a cosmic sweet spot where complexity can emerge. Some theories go deeper, proposing that 3-dimensional space arises naturally from the mathematics of quantum fields or the geometry of spacetime itself. It's as if the universe chose this configuration because it allowed for the richness we see today: stars, planets, and the very conditions for life. Yet the mystery isn't fully solved. Could there be regions of the cosmos where dimensions unfold differently? Or is 3 truly the only viable option? Whatever the answer, one thing's clear: our 3-dimensional world isn't just an accident, it's a foundational feature that makes the universe as we know it possible. And this leads us to our next head-scratcher. Could the universe be caught in an endless cycle of birth, death, and rebirth? The answer might reshape our understanding of time itself. Now let's turn our attention to a wild idea. What if the universe isn't a one-time event but stuck in an endless loop of rebirth? The cyclic universe theory suggests just that, proposing a cosmos with no true beginning or end, only perpetual cycles of expansion, collapse, and renewal. One version of this idea is the ekpyrotic model inspired by string theory. Picture 2 parallel branes. Think of them as giant cosmic sheets floating in higher dimensional space. When they collide, the energy ignites a Big Bang-like event, creating a new universe. The cycle repeats as the branes drift apart and eventually crash again, over and over. Unlike the classic Big Bang, this model avoids an initial singularity, replacing it with a collision that jumpstarts each new cycle. Then there's Roger Penrose's conformal cyclic cosmology, which proposes that the far future of our universe, a cold, empty expanse of scattered particles, could somehow reset into a fresh Big Bang. How Penrose suggests that as the universe stretches to infinity, particles lose their sense of scale, making the end resemble the smooth, hot soup of the beginning. His controversial evidence, strange patterns in the cosmic microwave background called Hawking points, which he claims are imprints of black holes from a previous cycle. But not everyone's convinced. Critics argue that the ekpyrotic model struggles to explain the universe's uniformity, while Penrose's Hawking points could just be random fluctuations. Plus, cyclic theories often rely on speculative physics, like undiscovered brane dynamics or untested quantum gravity effects, leaving big gaps in the story. Still, the allure of a cyclic universe is hard to ignore. Imagine a cosmos where every ending births a new beginning, stretching time into eternity. Whether it's true or not, the idea forces us to rethink our place in the grand scheme. Are we just one chapter in an infinite cosmic saga? And speaking of time's mysteries, let's peel back another layer. What is quantum foam, and could it hold secrets about the universe's tiniest building blocks? Now let's zoom in way into the very fabric of spacetime itself. At the smallest scales imaginable, where distances shrink to a trillionth of the width of an atom, spacetime isn't the smooth, stretchy sheet Einstein described. Instead, it's a bubbling, frothy chaos known as quantum foam. Picture an ocean during a storm, with waves crashing and bubbles constantly forming and popping. That's spacetime at the Planck scale, a turbulent dance of tiny, fleeting wormholes, twists, and voids that appear and vanish in fractions of a second. This isn't just theoretical poetry. Quantum foam emerges from the marriage of quantum mechanics and gravity, two forces that famously refuse to play nice in traditional physics. At these unimaginably tiny scales, Heisenberg's uncertainty principle means energy and spacetime itself can't sit still. Virtual particles and mini black holes blink in and out of existence, warping the fabric of reality in ways that challenge our understanding of empty space. So how does this quantum frenzy connect to the cosmos at large? Some scientists speculate that these microscopic fluctuations could seed larger phenomena. One wild idea suggests that the energy of quantum foam might contribute to dark energy, the mysterious force speeding up the universe's expansion. If spacetime's tiny bubbles store energy, they could add up across the vastness of space, pushing galaxies apart. Other theories explore whether quantum foam's chaotic nature could resolve the infinities lurking inside black hole singularities, smoothing out the violent spikes in gravity that break physics equations. But here's the catch: we can't see quantum foam directly. Probing the Planck scale would require a particle accelerator the size of a galaxy. For now, it's a ghost in the equations, hinted at by paradoxes like Hawking radiation or the holographic principle. Yet, even as a placeholder, quantum foam forces us to ask, is spacetime truly fundamental, or just an emergent property of something deeper? And if spacetime is more like a choppy sea than a flat pond, what other cosmic mysteries might ripple from its depths? That's a question that takes us to the next frontier, where the universe's magnetic fields weave their invisible threads through the void. Now let's turn our attention to something just as invisible but equally powerful: the magnetic fields that stretch across entire galaxies. These cosmic threads might not be something we can see with our eyes, but they shape the universe in ways scientists are only beginning to understand. The story starts in the early universe, when everything was a superheated soup of charged particles, a plasma buzzing with energy. In that chaos, tiny magnetic fields could have flickered into existence, sparked by the turbulent motions of particles or even remnants from the Big Bang itself. Think of it like stirring a cup of coffee. Wherever there's movement in charged particles, magnetism follows. But how do those weak, primordial fields grow strong enough to stretch across light years? That's where galactic dynamos come in. Picture a giant cosmic generator powered by the rotation of galaxies and the churning motion of their gas clouds. Over billions of years, this motion can amplify those faint magnetic fields, twisting and stretching them into vast, organized structures. It's like spinning a tiny magnet inside a coil of wire, except on a scale so massive it shapes entire galaxies. These magnetic fields don't just sit there quietly. They influence how stars form by controlling the collapse of gas clouds, and they guide cosmic rays, those high-energy particles racing through space. Without them, galaxies might look and behave very differently, yet mysteries remain. Why do some galaxies have stronger fields than others? How do these fields align so neatly across such enormous distances? Each discovery peels back another layer, showing just how much we still have to learn about the invisible forces weaving through the cosmos. And that brings us to the next puzzle: why the universe's expansion might not be as uniform as we once thought. But here's something that might make you question everything we thought we knew. What if the universe isn't expanding the same way in every direction? For decades, scientists operated under the cosmological principle, the idea that the universe looks roughly the same no matter where you are. But recent observations are shaking that assumption to its core. Take the Hubble tension, for example. This puzzle comes from two different ways of measuring how fast the universe is expanding, and they don't agree. One method uses nearby supernova, while another relies on the cosmic microwave background, the afterglow of the Big Bang. The numbers should match, but they're off by just enough to keep astronomers up at night. Some say it could mean dark energy, the mysterious force speeding up the expansion, isn't uniform. Maybe it's stronger in some regions and weaker in others, like patches of thicker and thinner rubber in a stretching balloon. Then there are the strange voids and superclusters, massive structures spanning hundreds of millions of light years. Could these cosmic neighborhoods affect expansion rates? Imagine blowing up a balloon with lumps in it. Some areas would stretch faster than others. If the universe has similar irregularities, it might explain why expansion rates seem to vary when we look at different patches of sky. And let's not forget dark energy itself. We assume it behaves like Einstein's cosmological constant, unchanging over time and space. But what if it isn't constant at all? Some theories suggest dark energy could evolve, growing stronger or weaker in certain eras or regions. That would mean the universe's expansion isn't just accelerating, it's doing so unevenly, like a car with an engine that sputters in some gears and roars in others. So where does this leave us? The cosmological principle isn't dead, but it's definitely on notice. Every new telescope and sky survey brings fresh data, and with it more questions. Could the universe be more chaotic than we thought, or is there a deeper order we haven't uncovered yet? The answers might rewrite our cosmic rulebook, and that brings us to the final frontier of our journey, peering beyond the edges of everything we can see. But before we close this cosmic journey, let's tackle the biggest mystery of them all: what lies beyond the edge of everything we can see. The observable universe stretches about 93 billion light-years across, but that's just a tiny fraction we're able to observe. Beyond that, the cosmos could be infinite, or it might hide realities we can't even imagine. One idea is the multiverse, countless bubble universes, each with its own laws of physics, popping into existence like foam in an endless ocean. Some theories suggest these bubbles collide, leaving scars in the cosmic microwave background, though we haven't found proof yet. Then there's the fractal universe hypothesis, where the cosmos repeats in self-similar patterns like a never-ending hall of mirrors. But here's the catch: we'll never know for sure. Light from beyond the observable universe hasn't had time to reach us since the Big Bang, and it never will, thanks to the universe's relentless expansion. It's like being stranded on an island, watching the horizon while ships sail away forever just out of sight. So what's out there? More of the same. A chaotic jumble of alien physics or nothing at all. The truth might remain locked beyond the ultimate cosmic veil, reminding us that some mysteries aren't just unanswered, they're unanswerable. And with that, we've reached the end of our exploration, but certainly not the end of the wonder. As we come full circle on this cosmic journey, let's take a moment to reflect on the 30 profound questions we've explored together. From the spark that ignited the Big Bang to the enigmatic dark energy stretching our universe apart, each mystery peels back a layer of existence, revealing just how much we've yet to uncover. These questions aren't just about science, they're about humanity's endless curiosity, our drive to make sense of the vast, swirling unknown. Whether it's the nature of time before the universe began, the hidden threads of dark matter weaving galaxies together, or the mind-bending possibility of parallel worlds, every puzzle reminds us how small we are and how extraordinary it is that we can ask these questions at all. So here's something to carry with you long after this video ends. Look up at the night sky tonight and let yourself wonder, what's your favorite cosmic mystery? Is it the eerie silence where alien civilizations should be? The way quantum particles defy logic, or the simple fact that any of this exists at all? Drop your thoughts in the comments. We're all stargazers here, trying to piece together the universe's grand story. And if you've enjoyed this journey through space's biggest questions, don't forget to like, subscribe, and hit that notification bell so you never miss our next adventure into the unknown. Because the cosmos isn't done surprising us, and neither are we. Thanks for watching and keep wondering.